Hi, my name is Richard. Today my topic is deep neural networking, machine translation and overview. So let's dive into the topic. Introduction to deep neural networking, machine translation. Deep neural networks have revolutionized machine translation by enabling more accurate and context-aware translation. These networks use multiple layers of interconnected neurons to process and learn complex patterns in languages. Deep learning has significantly improved the quality of machine translation systems over the traditional approaches. Neural machine translation. Neural machine translation is a type of machine translation that uses deep neural networks to translate text from one language to another language. NMT models are two end-to-end systems, meaning that directly translate a source language to target language sentences. NMT models have shown superior performance compared to traditional statistical machine translation approaches. So let's give an example. If any language is, if any system is want to translate one language to another language, it uses NMT, neural machine translation. So it uses deep neural networks to translate from one language to another language. So these are connected from end-to-end systems, meaning they directly translate source language sentences into target language sentences. Next, encoder decoder architecture. So encoder decoder architecture is a fundamental design in NMT where the encoder processes the input sentence and decoder generates the output sentence. The encoder converts the input sentence into pixel length vector representation, capturing the semantic meaning of the input. The decoder uses this vector representation to generate the output translation one word at a time. So in diagram you can see the encoder processes the input sentences to have the encoder vector for the fixed length of vector, and decoder gives the output one word at a time to representation, the vector representation, to generate output translation. So it is used in the fundamental design of NMT. Attention mechanism in NMT allows the model to focus on different parts of the input sentences by generating each word of the translation. This attention mechanism helps overcome the limitation of fixed length vector representation in encoder decoder architecture by attending to relevant parts of the input. The model can generate more accurate and fewer translation. Training deep neural networks for machine translation. Training deep neural networks for machine translation involves feeding parallel source and target language sentences into the model. The model learns to minimize the difference between the generalized translation and the target translation using optimization techniques like backpropagation. Large-scale parallel corpora are essential for training deep neural networks effectively for machine translation tasks. Challenges in deep neural machine translation. Deep neural network machine translation models require a large amount of training data to learn effectively, which can be challenged for low resource languages. Handling out of vocabulary words or rare language phenomena poses challenges for NMT models. Maintaining context and coherence in translations for long and complex sentences remains a challenge for deep neural networks. So you can see here input layer, hidden layer 2 and output layer. Input layer contains patterns of local contrast. Hidden layer 1 contains features, into layer 2 contains face and output layer. Transfer learning in machine language. Transfer learning techniques can be applied to machine translation by pre-training models on a large dataset of in one language pair and fine-tuning on a smaller dataset in different language pair. Transfer learning helps improve the performance of machine translation models, especially for low resource languages. By transferring knowledge from high resource language to low resource language transfer, bridge the data scarcity gap. You can see the diagram source or task or domain model. knowledge to model to target task or domain. This is the framework for learning. Evaluation metrics translation. BLEU, bilingual evaluation understood, is a widely used metric for evaluating the quality of machine translation outputs by comparing them into human reference translation. Other evaluation metrics include Metator, TR, and ROPE, which provide complementary perspectives on translation quality. Human evaluation remains crucial in assessing the fluency, coherence, and accuracy of machine translation outputs. So next we can see recent advances in deep neural network machine translation. Transformer models such as BERT and GPT series have shown significant improvements in machine translation performance by leveraging self-attention mechanisms. Multilingual models trained on multiple languages have demonstrated the ability to translate between language pairs not seen during training. Zero-shot and few-shot translation approaches and are emerging techniques that enable translation between language pairs with minimal or no parallel data. Next, ethical consideration in machine translation. Ensuring accurate and culturally sensitive translation is crucial to avoid perpetuating biases and stereotypes in machine translation outputs. Transparency in machine translation systems is essential to understand how decisions are made to others and potential biases. Protecting user privacy and data security in machine translation services is a paramount to maintain trust and ethical standards. Real world applications of deep neural network machine translation. So, machine translation technology is widely used such in online language translation services such as Google Translate or Microsoft Translator. In the healthcare sector, machine translation facilities communicate between healthcare providers and patients who speak different languages. Deep neural network machine translation is applied in international business, diplomacy, and global collaboration to overcome language barriers. In real world, we can use our Google Translator and Microsoft Translator. And in health sector, we use machine translation for various communications for to doctor and patients who speak different languages. And we can use in international business purposes and global collaboration to overcome language barriers. Future trends in deep neural network machine translation. Continued advancement in deep neural architecture and training techniques are expected to further improve the quality and efficiency of machine translation systems, integrating multimodal input such as text and images into machine translation. Personalization and adaptation of machine translation systems, user preferences and writing styles of potential future directions for research. Scalability and efficiency of machine translation models. Developing lightweight and efficient machine translation models is essential for real-time translation applications and resource concentrated devices. Techniques like model derivation, pruning, and quantization can help reduce the computational complexity and memory. Footprint of deep neural network models. Scalability and distributed training frameworks enable training large-scale machine translation models on cloud infrastructure efficiently. Interpreting and visualizing deep neural network machine translation model. Interpreting the decisions and inner workings of deep neural network machine translation models is crucial for understanding model behavior, improving transparency. Visualization techniques such as attention maps and heat maps can provide insights into how the model aligns source and target language words during translation. Visualization techniques such as attention maps and heat maps are the visualizing of deep neural machine network translation models. Interpretability to help identify errors, biases, and areas for model improvement in machine translation systems. Domain adaptation and specialized machine translation. Domain adaptation techniques enable machine translation models to specialize in specific domains such as legal, medical, and technical translation. Customizing machine translation systems for domain-specific vocabulary, terminology, and style can have enhanced translation accuracy and relevance. Specialized machine translation models tailored to specific domains can outperform general purpose models in coursework. Zero-shot machine translation refers to translating between language pairs without any parallel training data with window. Few shots and meta-learning cross-lingual translation techniques in machine translation by leveraging shared representation across languages. Multimodal machine translation. Multimodal machine translation integrates multiple modalities such as text, images, and speech to improve translation accuracy and context understanding. Combining visual and textual information can help disambiguate translation ambiguities and provide richer context for accurate translation. Reinforcement machine language can be used in fine-tuned machine translation models optimizing translation metrics directly. Reinforcement learning techniques can complement the supervised learning approaches in machine translation. Adapt the model to specific evaluation criteria. Addressing biases in machine translation, ensuring fairness and inclusivity in translation are ongoing challenges in the field. Conclusion: deep neural network machine translation has transformed the field of language translation by enabling more accurate, context-aware, and efficient translations. Continued research and innovation in deep learning architectures, training techniques, and evaluation metrics will drive further advancements in machine translation and machine translation technology efforts, addressing ethical consideration, improving scalability, and exploring new applications will shape the future of language translation. Thank you.